Hello, everyone. Again, let's finish up chapter 8. At least some of the discussion I wanted to do pertaining to it. Let's look at those 4 problems right there. Let's knock them out. Let's see how it goes for us. Let's see where we are here, guys. For problem number 27 in chapter 8 of the Katz book, a spring of spring constant K lies along an incline as shown. A block of mass M is attached to the spring compresses, and the block comes to rest as shown. Find an expression for the change in the earth block spring system's potential energy in terms of the parameters given in the figure. This is a lot easier done than said. I mean, it's a great question. The question itself, through nobody's fault, can be a little confusing just by the wording of it. Let's try to make it pretty reasonable how they're doing this thing, guys, how they're actually talking about it. Essentially what they're trying to say is, so they're trying to basically say here, find an expression for the change in the earth block spring system's potential energy. The change in the earth block spring system's potential energy. The change in the earth block spring system's potential energy in terms of the parameters already given. All right, guys, gravitational potential energy decreases, but spring potential energy increases. So kind of just watch it. What they got going on is that's theta. Here's the spring. The spring ends up gets compressed all the way to here. That's mass M. Don't know what to say here, guys. I almost want to do a different. This is let me just try to look at it. What it was, and so this is where it ends up, guys. And this is where it was. It's one block, okay? It's one block, so please let's not confuse that. Here, the yellow is where it was, and the white is where it's going to be. So, let's look at something like that. The distance from here to here is L. Similarity of triangles tells us that's the reality. If that's L, if this whole thing is L, then if this whole thing is L, this is L cosine theta, this is L sine theta. It drops by this amount. It's going to drop by that amount. So that amount of a drop that's going to take place, you guys, drops by this much, thereby decreasing gravitational potential energy. So the change in potential energy it dropped L sine theta. It lost L sine theta. So it dropped mg L sine theta. Remember, mgh, so negative mg L sine theta is the drop. Yes, but the spring gains this much potential energy. So you're just looking at that. I don't know if I can say I'm crazy about this, but yeah, I mean this is actually a true story. There's much more that goes into this to look at it. To make a long story short, the the change in potential energy is given by this. They leave it at that. If I was doing this problem, I don't want to say anything too bold here, to be honest with you, but the change in potential energy, let me try to think about this for a second. This would be mg mg sine theta times L. That's the amount of compression. There should be no change in potential energy, generally speaking, here, you guys. The loss in the loss in gravitational potential energy should be exactly the gain in spring potential energy. If this was a frictionless system up here, if you took this mass right here, held onto it, stretched it out this way, whatever it's saying on that now, let's see here. Well, they didn't, they sure didn't tell us a whole lot on this. Trying to think here. There's a lot more going on. There's a lot, if the spring right here was at zero compression, zero compression and zero stress, zero stretch and zero compression, this thing's going to cave in like this. There's going to be a loss of potential energy, but that loss of potential energy will go into the kinetic energy right here. If this thing has been stretched, there's a lot going on here. There's a lot going on here. They didn't really. There's a lot more that potentially could have and should have been said. The spring compresses and the block moves to rest as shown. Okay, so yeah, the spring compresses and the block moves to rest as shown. Okay, a block of mass M is attached to the spring compresses and is, okay, so yeah, here it was zero. Here it was zero, you let it go, it compresses. Theoretically, this would oscillate along the inclined plane if there was no gravity whatsoever, if there was no friction whatsoever. It would oscillate indefinitely in simple harmonic motion. There'd be periodic motion, and this would just oscillate indefinitely. It would be perpetual motion. People say, well, how can that be? How can it keep doing that forever? Does that mean there's an infinite amount of energy in there? No, the energy is stored in the system through the oscillation. As soon as it hits something, it won't do that. It can be brought to a dead stop. But that's one way it can store the energy. If there was no friction whatsoever, and it says they compressed it. There's a lot they didn't tell us. We're assuming there's no friction whatsoever. It's not mentioned to us at all. No friction whatsoever. If there's no friction and you compress this thing, then let it go. It's going to go up to its maximum height. What is the maximum height it's going to go to, and then be at rest for a second? So that the attach comes to rest as shown, and then after it comes to rest, there's a lot of ways you can write this, guys. If it comes to rest, what do they mean permanently comes to rest? Is there friction here? I don't want to get into this. I mean, there's a lot of ways you could write this. I've seen it written different ways. I think this is the way the book writes it in the notes here. You could say if it did come to rest right here, it'd have a lot of potential energy as far as gravitational potential energy, but it may not have any kind of potential energy regarding the spring. There's so much that we're not being told. We're going to assume, just to make this thing logical, my judgment call on this one, and I'll always tell you this kind of stuff. It's something that's kind of sensitive for an exam or something like that. Just follow the way they got it closely as possible, what they're saying to us. If it comes to rest right here, I'm going to say it comes to rest momentarily. There is perpetual motion in a sense right here, but before I even say that, there's no friction. So in this case, theoretically, there'd be perpetual motion if there was no friction. It'd come up to here, momentarily come to a stop, and then go downward. Hit again, and then come back up here. Back and forth this way. Okay, indefinitely. That's 27. 49, let's take a look at it. All right, 49 is saying, a roller coaster track is being designed so that the roller coaster car can safely make it around the circular vertical loop of radius capital R, 10 meters. Radius capital R equals 10 meters on the frictionless track. The loop is immediately after the highest point in the track, which is a height h above the bottom of the loop. What is the minimum value of h for which the roller coaster will barely make it around the vertical loop? Well, these guys are trying to live on the edge here, I guess. Let's make sure they get, they're going to safely make it, and they're trying to say it. Well, the way they drew it, a roller coaster track is being designed so that the roller coaster car can safely make it around the vertical loop of a radius, capital R equals 10 meters of frictionless track. The loop is immediately after the highest point of the track. What is the height of the highest point of the track that'll make that work, guys, is what they're trying to say there. So what they're saying here is, okay, that's a horrible drawing, guys, but let me see what I can do. A little bit better. This is capital R. Yeah, I know. I got news for you. So is that right here. So it's capital R up here, and it's capital R to go down there. The radius is 10 meters. 2 times the radius is that height, which is 20 meters. Okay, well, yeah, so nice little exercise there. This guy is the mass M. This is okay, so we got H is right there. We assume that the car has no kinetic energy. We're assuming that the car starts here at a dead stop. The car starts here, the roller coaster car starts here at a dead stop, which means has no kinetic energy initially. It's given a slight push and it just kind of goes in free fall. Has no kinetic energy at the top and then goes into free fall. And let's just take a look at it. If that's the case, you guys, haven't I already told you yeah, I mean, we've been there. We've done that. See how good that looks, you guys. Give me 1 second here. All right, not too bad. It's looking like that. What does that mean? Well, that means way on top, you guys, this guy's got potential energy, mgh. We already made the assumption that there's no kinetic energy. There's no kinetic energy initially present. The only energy present in the mechanical sense, no kinetic energy initially present in the mechanical sense. The only mechanical energy present initially is mgh. It's all potential energy, no kinetic energy. At the very bottom, see what we got here, guys. Let me try to think. Just trying to make them speak in their language. You don't want the guy to. You don't want them to fall out. So you want it to get. You want it to stay up there, and you're assuming that assuming that they're doing this with a car with nobody in there, obviously, or they got crash dummies in there and they're strapped in. So the crash dummies are associated as being part of the mass of the car itself, and how is it going to stay there? So the potential energy for the yellow, so this guy's all potential energy right here. That's all potential energy associated with all that. And this is the potential energy associated right here. So, you know, there's, I do and I don't want to write this. I mean, you could say MGH right here, associated with what's going on here. And then right here, this is another MGH, but the MGH here is MG, the height, this is 2R. So you got MGH, you got MG2R right there. And it's going to be going fast. So MG2R plus 1/2 MV squared. Okay. That's it. That's where you're going to find it. Let's go. The initial is only potential energy, but a lot of potential energy. H is high. The final, you got potential energy, just ain't as much. Well, what happened to the initial potential energy? Well, I'll give you some potential energy, but it's not the same as the initial. All this potential energy went into smaller potential energy, and the rest of it went into kinetic energy. If that's the case, we got to try to find the velocity here or something, or, well, we got to find a lot of stuff here. Let's see what we can do here. We could say, so this gets kind of interesting. We can see what we can do here. Now we got to find this out. We got to find out what's going on here. We're kind of in a bind right here. Yes and no. What's that going to be? Well, let's go slowly here. 1/2 MV squared. Subtract MG2R on each side. MG2R. So MGH minus MG2R. MGH minus MG2R, why don't you write it like that? Why don't you multiply by 2 and divide by M? Multiply by 2, divide by M. Okay, sure, believable. And it's believable. We're not done, but it is believable. So what we have here, let me just make sure the sound quality is good, guys. Okay, now we're okay, I think. I was a little worried on the last video. I was running out of battery time. We'll see how that worked out. I think the lion's share of it should definitely be on there for you to be able to see it. We've got this. Great. Okay, that's, I guess you could say that's an equation. It's definitely an equation. There's no I guess about it. There it is. And there's going to be another equation I think is going to help us out. And that's this. At the top of the loop, the goal is for this thing to stay on the tracks. It's not tied on the tracks by any way, shape, or form. This thing's got to be going fast enough that gravity is kind of the thing holding it up there. This tendency to want to fly outward is balanced by gravity, and gravity is as much of the pull there as we're doing this. So let me see here, guys. All right. So as this thing whips around, we know we know that mv squared over r, see, I care now about the loop right here, this loop, whatever it is, r. There's a tendency, made up force or not, of mv squared over r that way, and mg pulls down, mg pulls down toward the earth, and mv squared over r is the quote-unquote centrifugal force, and they're going to balance out. If you allow me to say it that way. What are we talking about? We're talking about that. Tell you what I'm going to do. Why don't you divide by m on each side and get rid of the m's? We did that over there. It worked the same way, didn't it? Divide by m on each side. Divide by m on each side and multiply by r. Hold on. We got two equations now. We got v squared equals gr, and we got v squared equals 2g times the quantity h over, we got two equations now. Equation number one, v squared equals 2g times the quantity h minus 2r, and we got v squared equals gr. So v squared equals gr and v squared equals 2g times the quantity h minus 2r. Wow, I think we're about to get it. Take these two equations and solve simultaneously. This is quite the interesting matter in this whole regard, for this whole thing to work out. You don't really need to know the v. You're saying, what are you talking about? The faster the v, the safer you are. Why don't I need to know the v? The v is already contained in the physics. The v is contained in mgh. 1/2 mv squared is mgh at the very bottom. 1/2, right at the very bottom, before this thing hits the loop, 1/2 mv squared is the kinetic energy, which is equal to mgh up top. mgh equals 1/2 mv squared. I could tinker with that a bit and get to where I'm going to go. It's going to work just fine. The speed at the top, I want to make this very clear. Okay, this is very important, actually. This is mgh potential energy, only potential energy, no other energy up here as far as mechanical energy is concerned. It's all potential energy, mgh. At the bottom, mgh potential energy is the total energy of the system, period. mgh. This is the total energy of the system, you guys. Simple as that, mgh. mgh, down here, there's mgh kinetic energy here. Yeah, mgh amount of kinetic energy called that h right here now. mgh is the same amount of kinetic energy right here. That's 1/2 mv squared. Yeah, but the difference in the two potential energies, the V I'm finding right here isn't 1/2 mv squared. This is 1/2 mv squared. I'll call it VI, the initial one. 1/2, or sort of initial, SI. 1/2 mv sub SI squared. 1/2 mv sub SI squared, that's equal to mgh. But once you go up here, it becomes V, and V is smaller because it climbed. 1/2 mv squared is equal to all of this potential energy minus all of that potential energy. This potential energy subtracted from that potential energy will give you the kinetic energy of the roller coaster at that instant. 1/2 mv squared is equal to mgh minus mg2r, which is mg times the quantity h minus 2r. That's 1/2 mv squared. That v is right here, not here. That's important. Not here. This is v sub SI. V sort of initial, which is the biggest one of all because it's mgh. mgh is 1/2 mv s sub I, 1/2 mv s sub I squared is what the mgh is. Here, It's less than that. I'm going to take the two V's, the two V squareds, and set them equal to each other. Let's see what we got here, guys. Let's just see how visible this is. Forgive me. Looks pretty good. V squared equals GR. V squared equals this. All right. Let's put the first one. V squared is 2G and the other one is V squared equals GR. It's pretty important. Let's see what we got here, guys. Probably a number of ways we could play this thing. Let's play it any way we want, I guess. Let's divide by 2G. Let's divide by the product 2G on each side. And we got H minus 2R. Divide by 2G on each side. That's R over 2. Add 2R on each side. H equals R over 2, which is 1/2 R, plus 2R. R over 2 is 0.5 times R. 2 times R is 2 times R. 0.5R plus 2R is 2.5R. At the end of the day, add them together, guys. 1/2 R plus 2R is 2.5R, which is 2.5R. 2.5R, they just told us R was 10 meters earlier, right? The beginning of the whole show, you guys, they told us that. 2.5 times 10 is 25 meters. This has got to be 25 meters tall, assuming a frictionless environment. If there's friction, it's got to be even higher than that, because friction is going to dissipate a lot of the work that's being done. A lot of the energy that's there is going to get lost to friction, if there is friction. If there's not friction, H is 25 meters, and you're going to be fine. Go to 77. All right, guys, 77. For problem number 77, a block. A block of mass M1 equals 4 kilograms, initially at rest on top of a frictionless horizontal table, is attached by a lightweight string to a second block of mass M2 equals 3 kilograms, hanging vertically from the edge of the table at a distance h equals 0.45 meters above the floor. If the edge of the table is assumed to be frictionless, what is the speed with which the block leaves the edge of the table? Meaning the top block. With what speed is it going to leave the edge of the table, you guys? What's going on here? So frictionless environment here, they gave us a few things to look at. Looking something like that. M1 is 4 kilograms. M2 is 3 kilograms. Right, M1 is 4 kilograms, M2 is 3 kilograms. The height above the floor is 0.45 meters. So, I don't know, guys, this is kind of obviously not the greatest drawing here. Maybe should have made these a little closer together. We're not going to split hairs on that. We're trying to find here that this right here there's a lot of assumptions being made here, I think. That's okay. I don't think nothing wrong with that. Let me think. So let me just... Right there, and it's going to fall this much. It's going to fall H equals this. We're assuming it's frictionless. We're assuming this pulley's somehow not going to get in the... Man, we got to make a lot of assumptions, but we're assuming the pulley's not going to get in the way, and maybe the pulley's lower in such a sense that it's not even going to hamper things. It's not really drawn that way in the book, but that doesn't matter. We can kind of use our imagination on this one. Pulley can be lower like this and then go for it. The thing's going to fly off the table. How fast is it going to fly off the table? It depends how fast they're all going. Depends how fast they're both going at the end of it. You got to remember something here, guys. The string is really light. Its mass does not come into play. The only two masses that come into play are M1 and M2. M1 is 4 kilograms. M1 is 4 kilograms. M2 is 3 kilograms. For all I know, this is 0.45. This thing, for all we know, could be 100 meters that way. It could be 100 meters to your left. That doesn't matter. The 0.45 meters, just the 0.45 meters, less than half a meter, that'll be enough to give this thing some kind of velocity. Once it gets that velocity, it ain't going to change. Why? It's a frictionless surface. Once it starts going at 30 miles per hour, it's going to stay going 30 miles per hour until it leaves the edge of the table. So let's just find out what the fall down is. How much speed is acquired during the fall down here, and how that's all going to work out here. All of the potential energy of the system will go into kinetic energy. All of the potential. This does not have, for us, I don't know what to tell you, this one. You can't really say it has potential energy because it is located somewhere. It's located high up somewhere. But I don't care. I only care right here. I want him to be brought to here. His potential energy does not get any smaller if he stays on level. How fast is that thing going right when it leaves the table? I didn't ask how fast it's going to be going when it falls all the way down. That's something there's other things I got to find out. I'd have to know how high that table is. I'd have to know how high that table is, and I'd have to know probably a number of things, actually. I'd have to find the components in two-dimensional space. Nobody's going there. They didn't go there. We're not going there. We are doing this, though. All of the potential energy of the system will go into kinetic energy if this guy's potential energy that's right here stays right here, stays on this level. If he falls down, that's a new game. That's a new ball game, guys. So all of the potential energy, based on what I just said, all of the potential energy of the system will go into kinetic energy. What are we talking about? I am basically saying this. This guy right here, that guy right there, its potential energy here, this is a better way to put it, this guy's potential energy, height h is 0.45. Here's h, so I'm just going to leave it as h for now. M2GH, all of that, when this guy hits the ground and falls down a distance h, when this guy right here falls down a distance h, M2GH, all that potential energy went into giving both of these masses, which are attached to each other, went into giving both of those masses kinetic energy that they did not have. These guys were initially at rest. Nobody was moving. I had my hand underneath here, then I took my hand away. The way they said it here. Let's just make sure here. At rest. So they're at rest. They're not moving. That's correct. All right. So when you look at that, solve for that. Multiply by 2 on each side and divide by the sum M1 plus M2. Multiply by 2 on each side and divide by the sum square root each side. What does that mean? It means 2. It means 3. That's 2. That's 3. This is 9.81. This is 0.45. 0.45 is the fall down length. M1 is 4. M2 is 3. That's it. Almost 2 meters per second. 1.95 meters. Yeah, right. 1.95 meters per second. All right, guys, let's go to 84. As of 2012, all the shuttles in NASA's Space Shuttle program have been retired. When they once launched a space shuttle, mass 2.03 times 10 to the 6 kilograms. That is 2,030,000 kilograms, you guys, would lift off as the thrusts of its 3 main engines was suddenly augmented by the firing of the solid rocket boosters at t equals 0 seconds. Suppose the shuttle's acceleration is given by a equals 3.00t plus 0.330 t squared minus 0.100 t cubed, where a is in meters per second squared, t is in seconds, in the first few seconds after lifting. This is in the first few seconds after liftoff. What is the change in the kinetic energy of the space shuttle during the first 3.50 seconds after liftoff in the scenario? The change in the kinetic energy after during 3.50 seconds, during the first 3.50 seconds of liftoff, what's the change in kinetic energy? This thing started with 0 kinetic energy. The astronauts, the joke I make on this, the astronauts don't jump into the spaceship as it's moving. The spaceship is stationary, obviously. That's how you enter a spaceship. That's how you enter a car. I don't enter a car as it's moving. I'm not James Bond. It's got to be stationary. If it's stationary, there's no velocity. No velocity means no kinetic energy. How much kinetic energy is there? How much kinetic energy is there after 3.50 seconds? Okay, so that's the question here for this whole matter. So let's take a look at it. So again, the final answer for 77 is down there. I think it should be pretty legible, guys. I'm trying to pick the best chalk I can for this whole thing. The speed of the item under consideration for problem number 77, the final speed here for our answer, our speed is v equals 1.95 meters per second. Okay. Looking at 84, what I just said, what's going on with this thing? All right, guys, there's the math. Shouldn't be too bad. Shouldn't be too bad at all for us. I mean, what we're doing is essentially this, guys. The way it's going to play out, for 84, they want the change in the kinetic energy. Well, the change in the kinetic energy regarding something that started with 0 kinetic energy because it wasn't moving. It started from the ground, where the astronauts entered the spaceship, the space shuttle, started from the ground. Nobody's moving at that point. The initial kinetic energy, this initial kinetic energy is 0, as we said. The change in kinetic energy is going to be the final kinetic energy after 3 seconds. That's going to be equal to 1/2 the mass of the space shuttle times that final speed that it attains after 3.5 seconds. The initial speed that this thing had, and I don't want to beat this into the ground, is this thing started on the ground. People had to get in. They had to prepare this thing. It's not moving. So V sub I is equal to 0. This is what I got to find. When I find this, that's really the final kinetic energy that runs the whole show. The initial kinetic energy, it ain't moving, so it's 0, as we said. The change in kinetic energy is that. So they're asking a bunch of things here, guys. What do we got? Well, let's find VF. We know what a half is. We know that the mass of the space shuttle is 2,030,000 kilograms. We don't know what V is, but once we know what V is, we square it, we multiply it by M and by a half, and we're done. Do you agree it started at time t equals 0, and it went until time t. There's an acceleration function, a, and we're going to integrate. We're going to have to, because it is variable. And here goes. Let's integrate. Part by part. The sum of the integral is the integral of the sums. This is plus a negative. Minus 0.1 t cubed is plus a negative 0.1 t cubed. Integrate them individually, like you were doing individual integrals. The integral of a sum is the sum of the integrals. Go for it. This is 3/2 t squared. This is, it's a long story. It's kind of, it's 0.11 t to the third. If you take the derivative of this, you'll get that. If you take the derivative of this, you'll get that. This one right here is negative, well, I'll tell you what we're going to do on this one. We're going to have to break it down a little bit. We're going to make it 1/4 the size of what it was before. To take this guy to the fourth. It's a bit of a mess, but we can do it. That's from 0 to some t. 0 to some t, huh? That means VF indeed yeah, for any value of t that you got. At t equals at t equals 3.5 seconds, VF equals, forgive me guys, let me just check how good that looks. It's okay, it's not great. We'll use something else. Put t equals 3.5 seconds. Put t equals 3.5 seconds in place of t right here, here, and here. See what it gives you. After 3.5 seconds, this is how fast it's going after 3.5 seconds. Great. The rest is right here, you guys. A half is a half. M is 2.03 times 10 to the 6th kilograms. VF is 19.34 meters per second. You'll end up squaring it. When you do all that, you plug in all the values here. Here's the half. Here's the 2.03 times 10 to the 6th kilograms. And here is 19.34 squared. Grind all that out and see where you are. And that's where the answer is going to be. The end of all that, you got this. You got KE equals a half times 2.03 times 10 to the 6th times the quantity 19.34 squared. It's going to be 3.796 times 10 to the 8th joules. That's crazy. That's a lot. That's a lot. They round that off a little bit, and there's stuff we got here on this, but I think the round off they gave, again, we're not going to nickel and dime this too much. I think the way the book gave the round off, somewhere there.